17 years, probably not, Liam, right? Okay, so still no calculator here, although we are going to have to get a little bit fancier with how we, in creative, with how we simplify things to make our life easier. But let me give you the scope of what related rates are. So in this situation, a pebble is dropped into a calm pond, causing ripples to form, ripples in the form of concentric circles. So you know what that would look like. You dropped I got no lead at all today. So I was just going to draw a picture. So draw a few concentric circles. Obviously, at the moment it hits, you don't have much of anything. And then as time goes on, you get multiple circles, and they get bigger and bigger. So the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So r doesn't equal 1. The radius doesn't equal 1. The radius is actually constantly growing. But when they give us the rate at which it's growing, they're giving us the rate of change of the radius with respect to time. So implicit differentiation is kind of not going away here, although rather than everything being with respect to x now, with related rates, everything is with respect to time. So the rate at which the radius is changing with respect to time is 1. That's the rate of change of the radius with respect to time. Specifically when the radius is 4 feet, so they're saying when the radius length actually is 4 feet, at what rate is the total area of the disturbed water changing? So they're looking for dA dt, the rate of change of the area with respect to time. If you think about this situation, if I go, like, let's say at the 1 second mark, the circle was that big, and at the second mark, it was that big. Is the rate of change of the area happening faster between the first and second? Or if you go out here, is it happening faster between the 1 second, 2 second, 3 second, 4 second, the 5th second, and the 6th second? Is the rate of change of the area happening faster in here or out here? No, there's an answer. It's not the same. All right, let's do it. So the area equals pi r squared. You have to know some of your formulas here. Okay? And then we're going to differentiate this with respect to time. So we're going to get dA dt equals, the derivative of pi r squared is 2 pi r, but followed up with a dr dt. So the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So that's constant. It'll be it's growing at a rate of 1 foot per second, whether you're in here at the 3 second mark or whether you're out here at the 5 or 6 second mark. So 2 pi r dr dt is definitely 1. So this is asking us specifically when the radius is 4. So we're going to use this formula and find the rate of change of the area specifically when the radius is 4. So to answer the question that they've asked, I'm just going to go with that. That's going to be 8 pi. And that's the answer to the question. The rate at which the total area is changing at the 4 second mark, or the radius of 4 mark, is 8 pi. So what is going to happen now if you are out further at like a radius of 6? What's the rate of change of the area going to be? If you plug in 6, it would be 12 pi. So the rate of change of the area is getting faster. Josh's logic was correct. Because as you go out, your radius is still increasing by 1, but your rings really are getting bigger and bigger and covering more area. Any questions on that? Okay, so when we read kind of these word problems, and this is just a basic one to start with, everything that they tell you, you've got to decide, is that the radius or is that the rate of change of the radius? Is that the area or is it the rate of change of the area, and so on and so forth. So before we get into multiple word problems, we're going to be a little bit more generic about it with these x's and y's. Assume x and y are both differentiable functions of t and find the required values of dy dt and dx dt. So there's two parts here. Here's the equation we're dealing with. We're first going to do part A, which is to find dy dt when x equals 3 and when dx dt equals 2. So everything is being derived in related rates with respect to time. So y's and x's both need a dy dt or a dx dt. So when I take the derivative of this equation, I think I'm going to distribute that too. First. Oops, minus 6x. And so when I derive, the derivative of y will be dy dt. The derivative of 2x squared will be 4x dx dt. And the derivative of minus 6x will just be minus 6 dx dt. So find dy dt when x is 3, so they're giving us that. And when the rate of change of x is 2. So 12 times 2 is 24, minus 12 is 12. Okay, so for B, similarly, I'm going to use the same thing here, the same derivative, but they're asking us to find dx dt, so the rate of change of x, when x is 1 and dy dt is 5. So dy dt is 5, x is 1, and I'm solving for dx dt, so what do I need to do? What do you think, Zach? Okay, yeah, I did that. So then what? To solve for dx dt. Right. Your minds are probably in the department of factoring right now. But truthfully, I have 4 of these minus 6 of these, so I also could just look at it as combining like terms, right? So there's negative 2, but if you factored it out, you'd get the same thing. Negative 2 dx dt, and then just divide both sides by negative 2. So the rate of change of the x coordinate with respect to t is negative 2.5. Questions? All right. Go ahead and derive this with respect to time on your own. Allie, tell me what you got. Perfect. And And then we just, for part A, we're just going to plug in what we know. So find dy dt when x is 3, dx dt is 8, y is 4, dy dt is what we're searching for. So this is all 48, so I'm going to subtract 48 from both sides. 8 dy dt equals negative 48. Divide by 8, and dy dt equals negative 6. Okay, for B, just use the same equation that Ellie derived for us, but just searching for dx dt. So when x is 4. Now, just out of curiosity, they didn't have, or just to tell you, they didn't have to give you y equals 3. If they didn't give you y, how could you find y on your own? Right. If they give you x is 4, your original, it has to be a point on the original. So if x is 4, you'd find that y is, I guess it would have to have been plus or minus 3, so that would have affected it. But just keep in mind, is sometimes if you feel like you're missing something else, you might want to go back and look at the other equations and see how we could find what you are missing. Negative 4 times 3 is negative 12. So if I add 12 to both sides, I get 8 dx dt equals 12. There we are. Okay? Not bad, just getting used to everything happening with respect to t. And then in this last section, a point is moving along the graph of the given function such that dx dt is 2 centimeters per second. Find dy dt for the given x values. So we need to derive dy dt equals, I'll do the quotient. Bottom times derivative of the top will cancel. Minus the top, so negative 1, times the derivative of the bottom is what, Haley? Good, Connor. You see that, Haley? 2x dx dt. And they're telling us in the beginning that dx dt is 2. Oh. You guys are the best. All over bottom squared. So in part A, we'll do part A. Negative 1 times 2 times negative 2 would be negative 4. dx dt, they're telling me, is 2 over 1 plus 4. Over 25. I want to take a look at this graphically so you can kind of wrap your head around what is happening, what all of these numbers mean relative to the graph. So give me 1 second. I squared the negative 2 first. You see that? Sorry, I did do a lot at once there. 1 plus x squared. Okay, here is the graph of this. I'm going to zoom in. Negative 3 to 3. Okay. So they're telling us that a point is moving along the graph of the given function such that the rate of change of the x-coordinate only is 2 centimeters per second. So I don't know if you want to look at that as 2 units per second, but this is the x-coordinate is changing at a rate of 2 centimeters per second. The actual speed of the point is then, in your opinion, going to be quicker where? Would it be quicker here if it does this stretch, or quicker here if it does this stretch? And why? If horizontal movement is 2 centimeters per second regardless, it goes from here to here in 1 second, let's say. And it goes from here to here in 1 second. Which one is it? Which one is the actual point moving faster overall? Take a stab at it, Liam. The second interval, yes, you're correct. Why? What made you say that? Correct. So it's traveling the same horizontal distance, but the vertical change is not much here. And in this stretch, again, the horizontal speed is the same, but the vertical change is faster. So in some weird way, it kind of reminds me of, like, if you're on that little spinny thing at the park. If you're standing in the middle and going around, you do one full circle in a second. This person on the outside does one full circle in a second as well. Yes? Who's obviously moving faster? The person on the outside, because they're covering more space in a different way. They're, even though they're both still going one full circle in a second. Anyway, so at -2, which is out here, the speed and the change of the y-coordinate, the dy dt, is 8/25. So we're going to look at 0 as well. So we're just plugging in to the same derivative that we found, -1. 2 times x is 0. dx dt is still 2. 1 plus 0 squared is just 1 squared. So this is all just going to give us 0. Which should make sense. The rate of change of your y with respect to time right at 0 is 0. Because we are flat. So our y coordinate speed is not changing at that moment. And at +2, we would get -1, 4, 2. Same thing we got the first time. -8/25, because that's symmetrical. So just to shed some light, so we just did the -2 and the +2. The graph's symmetrical, so the only difference is this one's positive, this one's negative. Okay? Just to kind of shed some light on what Liam said. So we just found it at +2. I'm going to find it at +1. And we should try to guess that this is going to be a bigger negative number. Yes? Because it's a little bit steeper there. So if I check that, I get -1, 2, dx dt is 2 still, over 1 plus 1 squared, so it would only be over 4. So we have -4/4, which is -1. So indeed, it's a stronger negative number. And faster. Okie doke. Okay. So if we look at the graph of sine of x, we're going to again derive dy dt. Derivative of sine is cosine x dx dt. And we're using that same preliminary information up here. The rate of change of your x coordinate, the speed at which our point is going to move horizontally along this graph, is 2 centimeters per second. So here's about pi/6, here's about pi/4, and here's about pi/3. Which one is going to provide the largest dy dt, do you think? This one out here? Yeah, I would say pi/6. A sine curve is the steepest as it's going through the midline. And then it starts to even out, and then it's still starting to even out as it approaches. So I believe our dy dt will be the largest here, and then it will be on the decline. But let's check it and confirm that. So dy dt is what we're looking for. So we have the cosine of pi over 6 times dx dt is just 2. What's the cosine of 30 degrees? Radical 3 over 2 times 2, and we get radical 3. If we do the pi over 4, cosine of pi over 4 is root 2 over 2 times the 2. We just get root 2, so it is on the decline. And then the cosine of pi over 3 times 2 is 1/2 times 2 is just 1. Okay? So just an introduction. We'll get into more word problems where this is really applicable to kind of the rate at which things are growing, volume, surface area, stuff like that. But the beginning parts are just getting used to this dx dt, following everything being with respect to time. Any questions? All right, well then you know what? I'll put your homework up.